Welcome to this lecture on mathematical methods. This is towards the end of the course and we learned many new things. We learned how to do calculus, which is essentially how to think about a function as a graph and then how to find derivatives and what is the meaning of derivatives, which is slopes and so on and so forth. And then we learned applications of this like diffusion and many other phenomena that we discussed, and we learned some statistics and probability distribution. Now, towards the end of this course, we would ask two questions, so that it will give us something beyond this course. This is an introductory course. So, beyond this introductory course, if you really want to do something for your research, how do we go about, what is the direction there? That is what this lecture will set. So, the title of this lecture is, it has two topics. One is hypothesis testing we will discuss, and mathematical modeling we will discuss. So, first we will briefly discuss what is the idea behind hypothesis testing like z-test and t-test. So, we'll only discuss the idea behind it, and of course, the details etc. would be discussed in a complete biostatistics course. And in the second part, we would discuss, given a phenomena, can we predict the probability distribution of some relevant quantities? Because we are always computing things from probability distribution, and now can we get the probability? How do we know what is the probability distribution given a phenomena? So, these are the things that we would try to answer. So, first let us discuss this thing called hypothesis testing. So, we will try to understand what is the idea behind hypothesis testing. So, let us think of a typical experimental phenomena that you would do, that you will have a set of population of cells or population of individuals, and you would want to test something. Let us assume that you want to test either a drag, effect of a particular drug in a population of cells, or some mutations or effect of a drug in a population of individuals. So, that's something that you would be typically testing. So, let us think of a population. So, this is a population of cells we are going to draw in this. So, this is population of cells without any drag. Equivalently, you could call it without mutation. So, this could be either without drag, and then you could have cells in another petri dish which will have similar number of cells. Now, after giving some drag, so you would add some drag here in this, some amount of drag, and here you will not have any drag, just the medium. Now, if you measure some quantities of this, like let us say if it is area or any quantity of gene expression of a particular gene in this population versus this population, you would want to test whether they are behaving similarly or differently. So, with and without drag, are they behaving differently or similarly? This is some obvious question that you would want to ask. Instead of this, you could think of a mutation and no mutation, right? So, you would have a population. So, you could have many examples. As we said, you could have drag. So, you could have without drag, drag minus, and with drag, which let me call this drag plus, and you could have wild type or a mutant. So, there will be always two populations. So, let us call this population 1 and population 2. So, you have two population, they are growing under, they are surviving, or they are growing under slightly two different conditions. If you measure any quantity, let it be gene expression, let it be the size, that would be anything that we quantitatively measure. Is there a difference between this and this? So, of course, if you could calculate the probability distribution, you can compare them. That is one way. We may not know what the probability distribution is. So, typically what we can do is compare the means. So, if you just look at the mean area of population 1 versus mean area of population 2. So, this comparison would give us some test and would give us some information, and whether these two populations are statistically similar or statistically different. If there is some difference, is the difference is statistically significant or not. We could think of many other examples, like so let us say we have temperature. So let us say we know that body temperature is normal body temperature is 37 degrees Celsius, let us say, and now you have 37.7 degrees Celsius when you measured. Will you call this fever or not? Right? Is this difference, would you call it fever? Is this difference statistically significant or not? Similarly, if you have such population and if you have such two population, which is drug minus and drug plus, you would want to measure some quantities, or wild type and mutant. So, it is always you will have a wild type and a mutant, and you measured some gene expression and you got here gene expression as 2 micromolar of protein being produced here. Here you got 3 micromolar. So, is this different? Is this very different, or they 2 and 3 are within the error? Is this difference statistically significant? Is this difference statistically significant or not? This is the question that we would want to answer, and for this you could just have a hypothesis test. For this people would use this idea called hypothesis testing. So, now what is hypothesis testing? So, first the hypothesis in this case, we would assume that the two populations are similar. We start with that assumption. So, that hypothesis is typically called a null hypothesis. So, you typically would start with something called a null hypothesis, and typically what this is, it says that there is no difference. So, that is both the populations are similar, there is no difference. That is the null hypothesis typically one would start with, which is called H0, which is null hypothesis. So, both populations, so which would also mean, either would mean the mean from the first population is equal to the mean from the second population. Or if this is a fixed value, sometime you would compare against a fixed value. So, 37 degrees Celsius fever is a fixed value. So, the x bar, you measure the temperature many times, and this is equal to mu, which is typically a fixed value, which is a standard value, which is, let us say, 37 degree, which is a typical standard value that you want to. So, either you want to assume that the measurement we got is same as similar to the standard value, so there is no difference, or these two populations are same. So, if you start with this assumption, that is mutant and wild type are the same. If you start with this assumption, either you can prove or disprove this assumption. Either you can validate the null hypothesis, or you would invalidate, you would reject the null hypothesis. So, we would always start with null hypothesis, and then we would proceed and either reject the null hypothesis or accept the null hypothesis. So, from data we would accept or reject null hypothesis. That is what we would do. Now, important point to remember is, for this what we are calculating the mean. So, and then comparing with either a standard value or with some other value of another population. So, we are always starting with mean. So, now what is the property of mean? We know that it is known that does not matter if you have a quantity, whatever you measure, the mean of that quantity will have a normal distribution. So, this is something that we mentioned. So, probability of mean of any quantity that you measure probability of mean of any quantity that you measure. So, that is P of x bar. So, you have x is the quantity that you are measuring, and so what we have x1, x2, x3, xn, and from this we can calculate x bar. So, you do measurement many times and you can calculate the mean or the average, which is x bar, and if you repeat this experiment many times, so let us say 100 many different people do this measurement n times, and we repeat this measurement and then calculate x bar. Many people can calculate x bar, and if we plot all this x bar, you would get a normal distribution. You will get a normal distribution, and the assumption is if n is very large. If n is very large, you would get normal distribution. If n is not very large, you will get something called a t distribution, which looks like a normal distribution, but of course this is slightly different. So, you would get for small n, you would get a t distribution. If large n, you would get a normal distribution. So, this is the first thing that we should remember, that if you have a quantity, so this is what is we are plotting here. This is P of x bar versus x bar will have a normal distribution if n is very large. If n is not that big, you will get a t distribution, which looks like this, but it has a slightly bigger tail. So, which is somewhat like that. It is also symmetric. If I just pardon me if I don't draw it symmetric, but this also is somewhat, this is symmetric. So, but the property is that this is t distribution. T distribution. T. The mean will have a normal distribution or a t distribution if this is n is very large. So, n going to infinity. If n is very large, you will have a blue curve, and n is very small, you will have a t distribution. So, this is the thing that we know. So, let us first think of normal distribution, then we will think about t distribution. So, you have, so let us think of situation first. We would do an experiment and we would do n measurements. So, what are we doing? We are doing n measurements. So, you have x1, x2, x3, xn, and from this you could calculate x bar, which is the mean, and you could calculate s, which is the standard deviation. And given this x bar, s and this n, we can calculate a quantity which is called the z or t, which is z, which is x bar minus a fixed number mu, which we already will have, s by root n. So this is, so let us say mu is like the 37 degree, the control number that we want. So we want to know that our number is comparable to the number that we have is a standard number or not. So we would calculate the z, same thing, same definition for t. And now the distribution of z or t would be a standard normal, the distribution of z would be a standard normal distribution. So what is a standard normal distribution? So it is known that P of z is a standard normal distribution. P of z is e power minus z square by 2, so 1 by root 2 pi. So what does it mean? Integral of this has to be 1, and this is a standard normal distribution. That means if I just have a distribution, it would look like a normal distribution with standard deviation is equal to 1, and so this is a distribution which has width, which is a sigma which is 1, and the mean is 0. So the mean is 0. So this is z bar. So this z bar is, the mean is 0 and the width is 1. So this distribution is called a standard normal distribution, and P of z will have this kind of a distribution. And now we can get the z quantity, which is x bar minus mu by s by root n, and we can calculate the z, and if x bar is equal to mu, if the measured quantity is very close to mu, you would expect a very small z value, or it could also be equivalently if you do large number of experiments or and so on and so forth. So depending on various things here, if x bar is very close to mu, z will be very small. So you think about this when z would be very small. So, but if z is very large, typically it would mean that x bar is much larger than, much larger than mu, and therefore z is very large. So depending on if the z is large or small, we would accept or reject the null hypothesis. So if z is very small, you can accept the null hypothesis. If z is very large, you would reject the null hypothesis. So look at this again. What is plotted here? What is plotted here is P of z. So now, what are we saying? We are saying that z could have any of this value. There is a probability of getting any of this value. But if you get a very large value of z, if you get a value of z which is very large, then which is very likely to be far away from the mean, very likely that your hypothesis, null hypothesis, can be rejected. But even if you reject it, there is some probability of getting bigger z values, these values. So your rejection of null hypothesis could be wrong, and there is likely to be an error in rejecting the null hypothesis. Even if it, so that error is this area. So this area beyond z value that you would get, this area beyond z is an important quantity called alpha, which is called a type 1 error. So this area is called a type 1 error. So what is type 1 error? So let us look at here. If we reject null hypothesis when it is true, the resulting error is the type 1 error. So let us take some numbers and explain this quickly. So we do some experiments and get an x bar, and we want to compare with some mu value. So we calculate this quantity z. So let us say you got 2.1 as the z value. So this is my z, and I got 2.1. And what we know is that the distribution of the z is a normal distribution, and this is 2.1, which is the z value 2.1, And since this is 0, since 2.1 is much larger than 0, since 2.1 is much larger than 0, very likely that x bar is far away from mu. But this whole distribution, the claim of this distribution itself, that z could have any of this value, the probability of z having this value is small, but there is some finite probability. So the probability for the z to have some value is 0, very small but finite. So there is a finite probability of having large z values as well. Therefore, if we reject this null hypothesis that H0 which says that x bar is equal to mu, if you reject it, if we reject, there is likely to be some error. If we reject the null hypothesis, there is some probability of getting some error. That probability, so the probability of having some error, there is some probability of having some error. So that error, and that error is nothing but this area. So the area beyond z is this error. This area beyond, so the smaller this area beyond z, the smaller will be the error in rejecting the null hypothesis. So if this area is very small, if z is very large, we can reject the null hypothesis. So typically this area you want to be like less than 5%, or there is nothing sacred about 5%. That is typically what one would want. So that is what typically one measures in this kind of hypothesis testing. There are a lot of details which of course cannot be discussed in one lecture, but I am just indicating you to the use of normal distribution. How do we use, what is the area beyond some value, what does it mean? Of course there is something, an alternate hypothesis, and depending on the alternate hypothesis one would decide you should take area on both sides, two-sided or two tails we should consider, and so on and so forth. Those are the details which you would learn in a statistics course, which is dedicated statistics course, which is a subject in itself. But the idea here is just to point you that if we understand normal distribution properly, and the area under the normal distribution, these are the ideas that is used in statistical testing, hypothesis testing, and we would want a z value which is large enough so that the area beyond that z value is very small. The area here is very small, therefore error in rejecting this null hypothesis. So the type 1 error, which is this area, so if we reject the null hypothesis when it is true, the resulting error is the type 1 error, and this type 1 error we want to be as small as possible, and therefore we would want z to be as large as possible, but it is up to us to decide how much error we can tolerate. If we can tolerate 5% error, we would be happy with it. If we want error to be super small, like 1%, we would reject it only if the z is very big, such that the area beyond that z value is less than 1% or so on and so forth. So this is the basic idea. Just remember, the aim of this short introduction about this hypothesis testing is not to teach you everything about hypothesis testing, but just to point you towards what is going on, just to make you, guide you towards it, where you should read more about this hypothesis testing in detail. Then the last part I would want to describe is equations for probability distribution. Given a phenomena, how do we get the probability distribution? So we do various experiments, and in all these experiments we do not know what is we measure some quantity and we do not know what is the probability distribution of that quantity. We are measuring some quantity x1, many times we measure xn. So some quantity x is what we measure, and we repeat it many times, and we measure n of this. We don't know what is p of x a priori. We don't know. We are not sure whether it will be a normal distribution, whether it will be what would be the distribution. It will be exponential. Whatever be the distribution, we don't know a priori. But can we know this? How do we know this? Can we use mathematics to know this? It turns out that it is possible, and people write equations for probability distribution. The way to do that is, so a lot of mathematical modeling is done to understand, to predict what would be the probability distribution given a phenomena. So the aim of this mathematical modeling is to predict P of x comma t, to predict, can we predict this given some phenomena. This is the aim of, this is what a lot of mathematical, ultimate aim of a lot of mathematical modeling. A lot of mathematical modeling is to, can we get this, or can we get at least for very large t. So when t is very large, that is, if you wait long enough, when it is steady state, where things will be independent of t, when things are in a steady state, can we get p of x. So these are the typical, either can we get p of x for any given time, or can we get p of x in the steady state. Steady state means t is very large and it's independent of time. It is not independent of the initial condition that you start with, it's just independent of time itself. So can we get this, and how do we do that? People write differential equations for t. So xp, so typically what you would write is, people would write equations like del p by del t. So we could write equations like this. For example, diffusion equation, like equations are typically used for random movements, random walks, or something is randomly moving and some quantity is randomly changing, then one would write equations like this, which is like the diffusion equation. There are equations like the master equations. So one would write dp by dt for some quantities. So if you have a polymer which is polymerizing and depolymerizing, and let n be the size of the polymer, Pn of t is the probability of having size n. What is the probability of finding polymers with n monomers? And we can write equations for such probabilities and solve those equations and get Pn. So this would give us, by solving such equations, one would get Pn. So such equations are typically called master equations. So mathematical modeling is basically writing equations for such Pn and probability distributions and then solving them to predict, to understand what would be the probability distribution given certain phenomena, and these equations will reflect the phenomena. So what is this equation that you would write down? It depends on what is the phenomena that we want to describe. So this is what one would do in an advanced mathematical modeling course, where one would learn how to write these equations and how to describe a phenomena given, how to write down equations given a phenomena, and how to understand, how to describe the probability distribution, etc., in terms of p of n or the p of x. With this summary, I would just stop this lecture, and this is the end of this course, where we want to conclude by saying that mathematics is again like a language, where we would learn how to describe various phenomena that we see around us, and the nature in general, like let it be whatever be the physical event, which is it could be in living science, life sciences, or any other branch of science and engineering. We could use mathematics as a tool to describe any phenomena that we see around us in a quantitative manner, and the things that we learned is the primary fundamental lessons on start thinking about how to use this mathematics as a tool to describe things around us. With this, I will stop here. Goodbye, good luck.